All right, so we're going to cover dimensional analysis. Well, what does the word analysis mean? What's it mean? It's like, do this analysis, right? Yeah, make some computations, predict some behavior, quantify. So that's analysis. Dimensional, so we're going to exploit casting results in dimensionless groups and extrapolating results from one set of conditions or experiments to another condition or set of experiments. So we're using the dimensional analysis, really. That's what we're using. So we'll have a quick review of dimensional homogeneity, talk about similarity between systems, geometric, kinematic, and dynamic similarity, and then talk about a procedure by which you can, in general, develop dimensionless groups, the Buckingham PI Theorem, and guide you in how to collapse data into a very compact, convenient form. Once you collapse it, then you generalize it, then you can uncollapse it or expand it and apply it to many different problems. Common dimensionless numbers like the Reynolds number, drag coefficient, lift coefficient, friction factors, correlations. Sometimes, well, you want to develop those correlations, and with those correlations, unravel them to predict the behavior of other systems. And then what happens if you don't have complete similarity? What happens if you want to extrapolate data or predict the behavior beyond what your data set was developed on? There are some times when it's a case where you have Reynolds number independence, meaning once you're above a threshold, if you continue to go up in Reynolds number, maybe that other parameter is constant, like a drag coefficient. Very handy. And that's the whole chapter on dimensional analysis. So it's needed or used because you're relying on experimental measurements. You make experimental measurements, they're very expensive, hence you want to extrapolate those to a wide variety of cases. You almost forget that that's what we're doing when you see it in practice, but there is a lot of thought and design behind dimensional analysis. So it clues you in on where to take measurements to guide if I need to predict a behavior in this range. Well, in my analysis, maybe I say I'll put this model together and then take measurements in this range. How to organize the data, especially in dimensionless groups. Then how to extrapolate the data and then unravel the data and predict the behavior of a real system. So a little review. We talk about primary dimensions and secondary dimensions. We talk about the SI units and the US customary units for each of those primary dimensions as well as secondary dimensions. A couple things. I think we've covered this. How many primary dimensions are there? Good, you can win a trivia question, right? 7. In all of science and engineering or just in engineering? All. The one that's least used by us, luminous intensity. The one that's most confusing to the double E's, hey, electrical engineering majors. You ask half of them, you understand about dimensions, primary, secondary? Yeah, I understand all that. Okay, which is the primary? Coulomb for charge or ampere for current? It's a trivia question. I'm preparing you for trivia. It's not a Coulomb is not the primary, even though you may have learned, and I learned, that an ampere is a Coulomb per second. So I suspect, although this is just my idea, is that it's much easier throughout the world to measure an ampere than it is to measure a Coulomb. Hence, that's the more primary. But I could be wrong. Somehow the international agreement is current, electric current in ampere is more basic than a charge in Coulomb. Amount, we don't use that much, but in moles, kilomoles. Temperature, we're starting to use a lot of these. And the big three that we use all the time, mass, length, time. Sometimes in this textbook, you have to figure out what are the symbols for each of those dimensions. Lowercase m, not to be confused with uppercase m. It's lowercase m for mass. L for length, lowercase t for time, uppercase T for temperature. N for amount, I for the current, and C for luminous intensity. All right. Secondary dimensions, there's a lot of them. Acceleration, velocity, area, force, and newtons, things like that. For the dynamic pressure, which is 1/2 rho v squared, fluid dynamic pressure we're going to see again a lot today. We saw a lot with Bernoulli's equation, 1/2 rho v squared. What is primary dimensions of that? Well, you can say that it's pressure, but we want to break pressure down. So if you break pressure down to mass, length, time, temperature, blah, 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 only using the 7, what do you get? Yeah. This is the way my brain works, because there's a difference between units, especially SI units, and dimensions. So we're looking for M and L and T, but I think it's awkward, at least for myself. So I think, Pascal. I know what a Pascal, Newton per meter squared. I know what a Newton is, kilogram meter per second squared. How do I know that? I just have it memorized. You just use it so often, it just rolls off your tongue. Isn't a Newton a kilogram meter per second squared? When did I learn that? I don't know. And then you may feel the same way. It's like, yeah, that's what it is. And so I work and think and talk in SI units, and then I want to put it back into the dimensions. So it looks like it's going to be a mass over time squared over length. Is that true? So the textbook also has, it's like P, and then it puts these brackets. It says, with the brackets, tell me the dimension of that quantity pressure. In a primary, it's mass divided by time squared divided by length. True? Did it make sense? Okay, and then the SI units for it, well, you could put Pascal, or you could put kilogram per meter second squared, something like that. Either one works. All right. Dimensional homogeneity. You use this all the time for error checking to help you detect when you make an algebraic error in a problem solving session. Basically, if I have a quantity A and I add to it a quantity B and that produces a result C, I can tell from this equation if it's dimensionally homogeneous, all the terms have the same. You can't add, let's say, a pressure with the velocity and get an acceleration. It doesn't make any sense. They all have to have either all of pressure, A and B and C are all pressure, or all velocity, or all acceleration, or all something. That's the concept of dimensional homogeneity. Let's apply that concept to this problem. The velocity profile is given by the equation U is equal to A plus C R squared, where U is velocity, R is radius. What are the dimensions of the parameter A, and what are the SI units of A? So, meters per second, the answer to the second question, what are the SI units of A? And then this is length over time. True? So that's the way. How many people find it easier to answer the second question first? Yeah, that's what I was trying to describe. I think more in the SI when I'm chasing down units and stuff. Then I have to say, oh yeah, L is for length, and lowercase m isn't for mass. Lowercase m, no, it is for mass. It's not for meter. Sometimes, it's like, is that m for meter or is that m for mass? Anyway, how about what are the dimensions of C and the units of C? So you can work it out slowly. You know that it is meters per second is equal to some unknown units for C times meters squared, because R is meters. Hence, it looks like it's going to be inverse meter second. So 1 over meter second, true. And then I put them back into the description of what are the dimensions. The dimensions are over length time. Some people will say, oh, well, it's L to the minus 1, T to the minus 1. Okay, great. Do it that way if you like. All right? Which term in this list is not dimensionally consistent with the other terms? Do not shout it out. I'll pause and walk around until at least 5 of you get it correct and I verify it. All right, so a lot of us worked it out that if it would have been a watt times a second, that would make it consistent. But it's a watt over a second. Just that little subtle slash made it the wrong, the correct answer, the one that's not consistent with everybody else. What's a Newton meter? A joule. What's a Pascal meter cubed? A joule. This one is what a joule is broken down, kilogram meter squared per second. And that's a joule. So this is B. Similarity. Well, you want to be able to scale between a model which you can think of as small, and often models are small, but they don't have to be. They could be larger than the prototype, the actual. This is the wording in the textbook. Okay? So the full scale is the prototype, and the model is the reduced scale. All right. So for similarity, you want the shapes to be the same, such that if you shrink the one dimension or length, then it's all shrunk, such that the areas are and the volumes are comparatively changed by the same dimension. All right. Then that's geometric similarity. Kinematic is velocity and accelerations. So does it have the same flow field around that object in the acceleration field? Is it scaled the same way? And then last would be dynamic force or moments of forces for that object. It's hard to have perfect similarity. Sometimes you get close to perfect similarity, but maybe you can justify why this isn't matched, but the results still are useful in predicting the behavior. All right. There's a lot in this whole topic and whole chapter, but I don't want to spend as much time on it because I need to move on to other topics in this class as well. We could spend more time on dimensional analysis. Let's introduce the method by which you can come up with dimensionless parameters. It's called the Buckingham PI Theorem or method. It's also the method of repeating variables. So what you do is when given a problem, here are the steps. Step 1, list all the variables and count them up, and there'll be n of them. Let's apply it to this problem right here so you can see it worked out. It says that the drag force on a sphere depends on the fluid velocity flowing over the sphere. So here's a sphere right here. And if the velocity of the fluid is coming at it, v is the fluid velocity coming at it, then you would expect to have a drag force, F of d. Okay. And it would depend not only on the speed of the fluid, it would depend on the fluid density, fluid viscosity, and the diameter of the sphere. This is a very challenging part. Is this list complete? Is something in it that shouldn't be in it? Or is there something that should be in it? Well, I'm going to say this list is complete for this problem, but when confronted with a new problem, you may struggle with what how many are there of these variables that come into play? And say for this problem, we have a F. We're looking for the drag force. We have V. We expect the fluid velocity. If the fluid velocity changes, we expect the drag force to change. We expect also the fluid density and viscosity. Maybe I'm running with air. Maybe I'm running with water. Maybe I'm running with glycerin or mercury, some other fluid. I may have the same approach speed. I may have the same diameter of the object. But if I'm running with air or water, it's going to greatly change the drag force. True? And then the diameter. If I change the diameter, that makes sense. Sure, it's going to have a larger drag force if I increase the diameter. That's my expectation. All right, so I count these, and we have 1, 2, 3, 4, 5. N is equal to 5. That's our number of variables. Then we break each one down to the primary dimensions. So D is a length. D for diameter is a length. So the primary dimension is just going to be L for a length for diameter D. Okay, now the next easiest one may be the mass density rho. This is our rho, right? Mass density. So what would be the, down to the 7, but often it's just mass, length, time. What is it in terms, density in terms of mass, length, time? M over L cubed? Good. All right. V. V for speed or velocity coming in. Is that length over time? True? And then now we're getting to where you have to work a little bit. What about that force, F? The force?
Mass, ML over T squared.
M L over T squared. That's what somebody suggests. Okay, what I'm going to do is I'm going to pause, and I want you to work out the force and viscosity in the fundamental, and I'll come around and check, okay? All right. So what did we get for the force? So is that mass, length over time squared? Thumbs up, you like it? Very good. And then what about the viscosity? Do we get the mass over length time? Mass for M, L for length, T for time? No, what did you get? You got what? Okay, you're thinking nu, which is mu over rho. And so this is what type of viscosity, and what type of viscosity is mu? This is the kinematic viscosity, and this is the dynamic, or sometimes absolute viscosity. Okay? So we did put mu for the dynamic viscosity. Is that the correct dimensions for the dynamic viscosity? Yes? Thumbs up or down? No. I got a couple votes yes. I got some people still looking. All right. I would say that's the correct dimensions. Now, what do we do is, for step 2, you determine all the primary dimensions and then count them up. And so what do we get for a count? J is equal to 1 for mass. Another 1, so that makes it 2 for mass and length. Mass, length, time, that's 3. Is there anything beyond that? No, so that's 3. Often in these problems, for this class, you'll just have 3. When you go to heat transfer, temperature and temperature difference. That's another one. That would be like J is equal to 4. Okay. The next step is you say how many pi groups or dimensionless groups do you anticipate? Well, take the difference. K is equal to N minus J, 2. I expect 2 dimensionless groups. What do you mean, Professor? Well, maybe one group I'm going to build around what I anticipate the result, I'm going to build around the drag force. I'm going to make that into a dimensionless group. And I'm thinking, as I increase something, maybe I can increase the flow of the speed at it, that the drag force would go up. See, I'm trying to think about the relationship. So if I increase the speed of the fluid flowing over the sphere, I would anticipate the general trend observed by experiments is the drag force would increase. Maybe it would level off. Maybe it would go like this. I don't know. I'm just trying to throw out some ideas. So what you do is you say, I need to build around two groups, dimensionless pi groups. Why not pick F to build around and something like V to build around? Now, I wouldn't pick V because I know the resultant F is a good one to build around because it's like get the drag force as a function of other things. But for what will go on the x-axis, pick something of the remaining four that look the most complex for the number of dimensions. So V is L over T. That's only two of them. D for diameter, the fifth one, is only time, T. That's only one parameter in it. What has the most? Mu. So pick this one. Why again? I'm trying to just say it has the most, most complex. Okay, now, so what do is we say, let's pick this one, and we'll call this the first pi group. All right. And you could start it with F, or you can start it with inverse F, but try not to get fancy. Just start it with something. Often it's just F. Now, right below it, I like to write out, I've got to scoot down. I'm so sorry. I've got to scoot down. Okay. I write down it's mL over T squared. Without using F again, and without using the second one parameter you're going to build around, the viscosity mu, don't touch it. Leave those alone. Only use the other three. And now I look at it and I say, I have a length over time, I have a mass over L cubed, or lengths cubed, and I have a length. Length appears in three of the three. Time appears in one of the three, and mass appears in one of the three. So either I get rid of the mass or time, but I try to get rid of the hardest one I anticipate to get rid of. So let's get rid of the mass first. If I can either multiply by rho or divide by rho to get rid of the mass. All right, if I divide by rho, it'll be mass L cubed. See that? And what happened to the mass? Goodbye. So I start building this dimensionless group by starting with F, divide by rho. Don't want to use F anymore, don't want to use rho anymore, don't want to use mu anymore. I have only two other parameters to use, V and D. All right, I need to get rid of that time. So should I take and maybe put V squared? That would be length. I was trying to write meters. Length squared. I've got to divide by V squared, don't I? Right? And that would be length squared over time squared. That says goodbye to the time squared. True? Good. Now I only have length, and only one left is D to get rid of the last of the lengths. So what should I do for this D? So I multiply by 1 over D squared. That puts 1 over L squared, and all of those cancel out at this point. There's a more algorithmic way, and I get three equations and three unknowns and solve for the A, B, C, and maybe B is -2 and maybe C is -1, but do it this way, I think. It's a lot of insight. It's easy. All right? So when I come up to this plot right there for this F of D, what I'll do is I'll plot the drag force divided by the rho B squared D squared. And now that's a dimensionless property on the y-axis. Make sense? Okay. Now let's build the next one. Let's start with the viscosity. So the second dimensionless group, I can either start with mu or I could start with 1 over mu. Since I said let's just not be fancy, let's just start with mu. So what are the units? Not the units. The dimensions of mu. It's mass, length, time. Great. I look at number 2, number 3, number 5. V, rho, or D. Which one? Let's use rho to get rid of mass. So if I divide by rho, then I have mass, length cubed. True? So the mass goes. Good. Now what do? Let's get rid of the time. How do I get rid of the time? I will divide by V. V is length per unit time. The times go. Now I have just lengths left. And if I divide by D, then it's a length. And they're all good. 1, 2, 3, 1, 2, 3. Right? So the second parameter is equal to mu over rho v d. Somebody says, hey, that's 1 over the Reynolds number based on the diameter, where the Reynolds number based on diameter is rho v d over mu. You're absolutely correct. Now, it looks like in hindsight we should have started with 1 over mu and we would have gotten the Reynolds number directly. That's great. But a dimensionless group is a dimensionless group. 1 over Reynolds number is just as dimensionless as Reynolds number. So when we come up here, you can put a rho v d over mu, and you just made that the Reynolds number for the x-axis. And this makes, I think, a lot of sense to us, because if you increase the speed, what are you doing to the Reynolds number? It's going up. It's going up. All right? And then if you increase this dimensionless parameter here on the y-axis, what's going up? The drag coefficient, larger drag. Faster, more drag. That seems to be the relationship. So in general, we would look for a relationship where the group pi 1 is a function of pi 2. We didn't say it's equal to pi 2. We said it's some function of pi 2. Maybe it looks linear down in this region, and then maybe it flattens off. I don't know. Maybe it comes down. Maybe the drag coefficient goes down and then tapers off. Could be some other relationship that we didn't know. But without going and making any measurements, this would guide us to say that functional relationship is this dimensionless parameter F, drag force, divided by rho v squared d squared, is a function of rho v d over mu. All right. So you picked your repeating parameters. You created that many pi groups. You finished it out. There's the example. Now, this one is a Reynolds number. We already were exposed to the Reynolds number. We can interpret the Reynolds number as the ratio of inertial to viscous forces or stresses or pressures. True? Maybe it's been a while. It was back at chapter 1. But when you see Reynolds number, it's a ratio of inertial to viscous forces or pressures. Now, what about this other? This is a drag coefficient. It's the drag divided by, could I put a 1/2 rho v squared and that would still be dimensionless? Is that 1/2 going to not make it dimensionless? No, it's going to make it dimensionless. What's 1/2 rho v squared called? 1/2 rho v squared. I haven't finished it out. Let me finish it out and put over here. Pi d squared over 4. Just like the pi and the 4 and the 1/2, they don't really change anything, but that 1/2 rho v squared is called the Make me feel like I've earned my pay somewhere, somehow. From Bernoulli's equation, we had the pressure form of Bernoulli's equation, P plus 1/2 rho V squared plus rho GZ. Rho GZ was some sort of hydrostatic pressure. P is the static pressure. 1/2 rho V squared, velocity or dynamic pressure. That's exactly it. That's what we're looking. You'll see that group of terms show up again and again and again. So it's like if I take this flow and I have a nice little line, a streamline, and I bring it right to that point, what did I do with the little chunk of fluid? I brought it to rest. And it's talking about the highest pressure you could ever expect, which would be the incoming static pressure plus the velocity pressure. Boom, you got the stagnation pressure. P plus 1/2 rho V squared. All right. So you'll see, we normalize it with respect to the velocity pressure. And then what about pi d squared over 4? What's that? Area. It's not the surface area of the sphere, but the flows coming at it, it's the projected, like silhouette area of the sphere, which looks like a disk, a black disk. Pi d squared over 4. Remember, it's not the surface area of the sphere. Oh, Professor, I forgot. What is the surface area of the sphere? This is a great clicker question. Is it 4/3 pi r cubed, or is it 4 pi r squared? Sorry, I don't have the clickers operational today, but either this or this is the area, and guess what? The other one is the volume. B is the area, and A is the volume. To help you, how many R's are in the top one? 3. How many R's are in the second one? 2. So length cubed versus length squared. Okay, very good. So what we have is we have some projected area, and we have then the velocity pressure. So to normalize the drag force, you just divide by the velocity pressure times the projected area, which is makes a force. You divide by another force. That's a drag coefficient. You have a periodic Karman vortex sheet is formed when a uniform stream flows over a circular cylinder. So here's my circular cylinder. I have a uniform flow approaching it. And what happens is at a particular speed of the flow over that cylinder, you get what they call a street, a group of vortices that are being shed. What's a vortex? Well, it's a pattern where the fluid is curling around like this. Okay, well, but maybe it's shed there, but before it shed from the top. And before it shed from the top, it shed from the bottom. And then before it shed from the bottom, so you get this street of shedding vortices that come off the back side of that cylinder. That's what they mean by this vortex street. Okay. And the guy that studied it is von Karman. So Karman vortex street. All right. Determine a dimensionless relationship for the vortex shedding frequency as a function of the free stream speed v, fluid density rho, fluid viscosity mu, and the cylinder diameter d. So what you do is when you want to solve this problem, you have v, you have d, you have frequency, you make a list of all of your parameters that have dimensions. So just using this notation, f of k, what is that? That is our vortex shedding frequency. Okay. Then another one is the speed of the fluid approaching, the free stream speed of the fluid. Then we have the density. Then we have the fluid viscosity and the diameter. And then we pause and we make sure that we have all of them listed or not listed? How many are listed? 1, 2, 3, 4, and 5. Then we have to break it down to the fundamental dimensions. Okay, something like v, the velocity, the second one, that's pretty easy. What is the fundamental dimensions with lowercase m for mass, uppercase L for length, lowercase t for time? Would that be for this v, for the fluid velocity? Is that what it would be? All right. Now, density, rho, that's probably just as easy. Is it mass per unit volume? All right. The diameter, I should have done that one. That's even easy. Length. Now we have to do a little work for this dynamic viscosity. The dynamic viscosity, so you'll have a mass, and then you'll have a length time. Is that what you said? Yep. So a mass divided by length time. And then go back. Vortex shedding frequency. Frequency. Is hertz a frequency? Like, say, 60 hertz? Yeah. And so what would be the units on hertz? Cycles per second. A cycle is dimensionless, but it's per second. It's per unit time. So it's per unit time. True? So what we do is we count these up and we say how many of these fundamental, the number of fundamental dimensions is equal to what? Well, we have mass, length, time. That's common for a lot of these problems. So there's 3. Mass, length, time. How many parameters are there? The number of parameters. That is 5. And so what we're looking for is we're going to look to build 2 dimensionless coefficients and to establish a dimensionless relationship. So the difference between 5 and 3 is 2. So that's the number of dimensionless groups or dimensionless parameters that we're going to be looking for. Well, we worked through and we said that there's a length, that's one of them. There's a mass, that's another one. And there's a time, and there's no others. So there's, I just visually counted them up. Last, I see I don't see a temperature, that would have added a 4th. I don't see an amount, that would have added a 5th. I don't see a candela, right? Luminous intensity. Okay, we get the point. We're often 3 or 4. Okay, so what you want to do is you want to pick which ones to build around. So at this point, we'll pick the frequency, add the viscosity. In general, pick the most complex of the individual terms or parameters to build around for a pi group. So here's my first dimensionless group that's going to be f of k. I know it's not complicated, but it's this another thing is I anticipate some sort of the frequency of the shedding as a function of things like the fluid viscosity or the speed or something like this. Viscosity of the fluid or speed of the fluid. And I'll measure that on the x-axis, and I'll have on the y-axis something I'm very interested in predicting, and that's that frequency of the vortex shedding. And maybe when the flow goes up, maybe when it's going faster over here and slower over here, maybe the trend is it's shedding slowly, and then it tapers off, and maybe sheds at a constant speed. Or maybe it does this. Maybe the pattern looks like that. I don't know. We have to go and we get experiments to confirm what the relationship is. So what we're going to do is we're going to build around f of k. So if I start and I have 1 over time, what do I do by using 2 and 3 and 5 to turn it into something dimensionless? This takes a little bit of practice, but if I try to multiply by row or divide by row, one of them, I'm going to introduce an m for mass, and then I won't be able to cancel it out. So don't introduce and multiply or divide by row. But I have 1 over time, so to get rid of the time, what can I do with the v? If I can multiply by v or divide by v. Which one do I want to do? If I divide by v, or multiply by 1 over v, then I'll have a time per length. See how we introduce that? So in my mind, I say, okay, the times are gone, that's great, but I'm left with a length. But I can use not the third, but the fifth parameter, d. And if I multiplied by d, that would be L. And we're done. F times d divided by v is a dimensionless group. And so on the x-axis, if I really wanted, the y-axis, when I get some experimental data and I want to generalize the results, I'd plot not f of k, like inverse seconds or hertz or something like that. I'd plot f of k d over v. It's a dimensionless group. Okay, let's finish out the second one, which will be plotted on the x-axis. So let's start with the dynamic viscosity mu. What is it? It's the mass per length time. Okay, I look at the second and third and fifth parameter and I say, I better use rho and get rid of the mass. So if I take and I divide by rho, that'll be mass length squared. True? Oops, length cubed. True? So that'll get rid of the mass, and I'm done with the mass. And now I have length squared divided by time. Let's get rid of the time by dividing by v. That will give length per unit time, like that. I cancel the time. And now I have length cubed over length squared, which is simply length. And so what do? I divide by d. And if I divide by d, I have 1 over length. And finally, all of the lengths cancel. True? This length, this length, this length, L cubed. So the second dimensionless parameter or group I would put on the x-axis, and it would be this mu divided by rho vd. Now, Professor, I like it when on the x-axis, if we push off to the right, and I'm thinking fluid flow, it's going faster and faster. But the way you put this, it's if v goes up, 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 this 1 over v goes down, down, down. It's dimensionless, isn't it? Yes, it is. Professor, can I do this? Can I put rho v d divided by mu and plot it that way? Yes, you can. And that parameter, or that group of terms, is out there in the literature. It's called the Reynolds number. The Reynolds number, which we were already exposed to, true? So sometimes it doesn't look like, oh, look, there's the Reynolds number. But if you look harder, you say, it's the inverse of the Reynolds number. Well, you started with mu. You could have started with 1 over mu, and then it would come out directly. Yes, sir?
When we're solving these, we're just trying to get it each one to 1?
No, they're dimensionless. And so when you put in, let's say you made some measurements, and maybe it came in to be 300. Okay, so this Reynolds number is 300. Then you come over here and you measure this FD over V. Maybe it was 40. And so then it's 340 and there's a plot. Maybe that's a data point. And maybe when it was 200, it was 30. Or maybe when it was... So you plot whatever the points are to see the trend in the data, in the relationship. But this dimensionless parameter spans from very, very small to very, very large numbers.
So since the fact that there's 5 parameters and 3 unknowns, and we know that there's only going to be 2 groups on the x and y axis, what if there was 3? Is there a different
Right.
system?
Yeah. No, you just have to then plot on here. If you had 3 pi groups, maybe this is, or groups of terms, this is the first one here, this is the second one here, and that one was for this value, and maybe this is range of increasing the third. That's how you plot it in 2D. Or you go to 3D and then you have a surface plot. But most engineers like multiple curves on a 2D plot.
Okay, so it'll be 3D, then 3 pi, it's 3-dimensional.
That's right. And then if you had 4, well, then you have more challenging. You could have 4 dimensionless groups.
Are you going to be making this? I don't get a question.
Yes, sir.
On your first pi group right there, I see you only used a B and D. On the second one, you used rho B and D. We don't have to use all 3 of them. We can just use as many as we want.
Yeah, that's correct. You want to spread them out, but basically, somebody else comes along and they see the red circled ones that were the starting point, the building blocks. Somebody else says, "Let's pick D and V." They're going to run into a little bit of a problem because is mass in either one of those? No. So there's a little bit of art to picking them so that you don't get in a bind. All right.
So maybe a less artful and maybe more systematic or algorithmic way to determine that.
Oh, the book has a very long write-up on that. It's a very good write-up on how to pick them, do's and don'ts.
Like Buckingham PI Theorem.
That's it. That's what we just did. I just introduced it, but I'm going to introduce it more formally.
So you said you could flip the Reynolds number?
Sure.
The first pi term?
Yeah, this group right here is the inverse of the Reynolds number. What?
The first part, can you flip that as well? Or just because it's the Reynolds number, you can flip it?
No, you could flip this too, but often is there a reason to flip it? And simply Reynolds and the history of fluid mechanics has this group of terms, and it's dimensionless, called the Reynolds number. And as the speed goes up, V, the fluid speed goes up, the Reynolds number goes up, not down. If somebody was start and said, hey, here's the definition of Reynolds number, and it's mu over rho VD, then the history would have taken us that way, and we would be accustomed to high speed flows have low Reynolds number. There's a lot of these established non-dimensional parameter, dimensionless parameters. We just explained one, the drag coefficient. It's that drag force divided by the velocity pressure, 1/2 rho v squared, times the area projected. You can even remember these things the way they're written. Okay. What about the lift coefficient? CL. Now, if I have an object, often if I'm interested in lift, it looks like a wing. All right. And I have fluid coming in toward the wing. Now, that wing could be oriented like this, or it could be oriented like, that's a bad looking. All I'm trying to do is tilt it. Let me try it again. See the difference? It's called the angle of attack. Let's not get confused about the angle of attack, okay? But let's just say for a fixed angle of attack, this object, which is supposed to give lift, will give a lift, and the lift is in the direction that is either perpendicular to the velocity coming at it, or it will give a lift perpendicular to the chord like from the tip to from the front to the back of the wing. So FL. So this is a little confusing for students, but let's just grapple with it. What do you think makes more sense? Do you think that the engineers who are going to talk about lift will do it where it's with respect to going from the tip to from the ends of this wing, and they have the chord length, and then the perpendicular distance or the perpendicular orientation or direction gives you the direction of the lift? Or do you think they put the lift with respect to the fluid flow? Okay, I'm not going to have you answer out loud. I want you to answer, and I'll walk around and see how you answer on your notes. All right, so the vast majority is you put the lift in the direction of the fluid flow. And then often what they'll do is they'll say, if I put and I change the angle of attack, my lift can go up, and then then I can get to where it doesn't lift anymore, and I've got big problem. Okay? The wing's not doing it anymore to help me. So that's often what they do. Is it's very, very common to put the lift with respect to the fluid. The air that you're cutting through is typically quiescent air. Okay, what then about the drag? The direction of drag is in the direction of the fluid direction across that object. Okay, so this is force lift. What do you think they do it? Let me put F of D for force drag. 1/2 rho V squared, that makes sense. It's the velocity pressure, dynamic pressure. But it's this area, it's a different projected area. It's like the plan form area. It's the downward projected area. So if I'm looking for drag, I look at this direction. For a wing, it doesn't have much area. But if I look down at it, guess what? That's a lot of area. It's a large area. Okay? So this is the different projected. It's downward. Plan form area, they call it. Okay. What about this Reynolds number, RE? It's rho V. Some length, often we'll put that RE, we'll repeat that L right there, REL over mu, or RED, and that will be rho VD over mu. It's whatever is that length scale, L, put an L there, or D for diameter, D there. So now, what is this rho V L over mu? Well, I think we talked about this a long time ago. It's a relationship between the dynamic forces or inertial forces to viscous forces. So if you have a high Reynolds number, the inertial forces or inertial pressures are high compared to the viscous forces or viscous pressure. So if a low Reynolds number, viscosity dominates. Euler number, well, it's just a parameter. So if I have a pipe and I have location 1 and P1 and location 2 and pressure 2, I could have a pressure loss in the length of that pipe. And so something like the initial pressure 1 higher than the outlet pressure 2, that's a pressure loss. But I have to normalize it. So what do I normalize it by? Well, since it's already a pressure, I just have 1/2 rho V squared. So the average speed V down the tube, or down the pipe. So what's 1/2 rho V squared? We use that so often. Is that used right here? Is that used right there? Is that used right there? Yeah, it is. What's the name of 1/2 rho V squared? Dynamic pressure, velocity pressure, something like that. It's think about Bernoulli's equation, and you take that kinetic energy and you convert it to pressure. It's that Bernoulli's P plus 1/2 rho V squared. Bring it to rest, you bump up the pressure by that amount. Okay, and there's many more, okay? There's a long list of parameters in the textbook, and when you get into a particular field of engineering, some dominate. How do we really use this information? Maybe I should go back here to this problem that we were solving. Maybe we find the relationship between the drag coefficient plotted on the y-axis versus the Reynolds number. And you make some experimental measurements where you have the geometric and the kinematic and the dynamic similarity. And you have plotted out some data points. And then for a new experiment, before you even conduct it, or maybe you don't even plan to conduct an experiment, but you want to predict the behavior of a new design, you would come in and say, well, I need the drag coefficient. We'll figure out what the design Reynolds number would be. Would it be right around here? Then come up and evaluate based on previous experimental data the drag coefficient. And then you could use that drag coefficient to predict the drag force for the new case based on previous measurements. So let's solve a problem. You have a 1/4 scale model of an airplane, but it's good to be tested in water. Well, there's no airplane that flies in water, but this is the type of thing that you can do using dimensional analysis. The airplane has a velocity of 700 kilometers per hour in air at negative 50 degrees C, high altitude. The water temperature in the test section is 10 degrees C. In order to achieve similarity between the model and the prototype, again, what is this model? It's the 1/4 scale. What's the prototype? The real deal, the full scale. All right. The test is done at a water velocity of 393 kilometers per hour. Properties of air, there they are for the density, viscosity at that prototype or real deal temperature and pressure. The properties of water under the test conditions, density and viscosity are given. If the average drag force on the model is measured to be 13,800 Newton, determine the drag force on the prototype. If I take the airplane and I'm flying it up there, what's going to be the drag force on that aircraft, the prototype? Then you know what the jet engine has to put out in order to keep it flying. Okay, so what we do is we think we have the drag coefficient is a function of the Reynolds number. We established that before. We think it'll be the same behavior. The drag coefficient's a function of the Reynolds number, and that's it. Okay. So in order to predict you think about applying this equation twice. The drag coefficient for the model is a function of the Reynolds number of the model, and the drag coefficient of the prototype is a function of the Reynolds number of the prototype. I don't know the functional relationship, okay? But if the Reynolds number of the model and the Reynolds number of the prototype are the same, that's a big if, what can I conclude about the relationship between drag coefficients?
You set them equal.
They're going to be equal because there's only one correlation in general. We have similarity. The geometric and kinematic and dynamic similarity we're anticipating or expecting, but definitely for the 1/4 scale, we have the geometric similarity. So if that's true, then these are the same. Okay, so let's go and check. What is my Reynolds number for the model? Well, the Reynolds number for the model is going to be some rho. Now, again, what is this model? It's with the water, isn't it? The velocity in the water, some length scale of the model divided by mu of the water. Okay. I could go over and I could say, well, what's the Reynolds number of the prototype? It would be the density of the air, the velocity of the air, the length scale of the prototype divided by the viscosity of air. I should have maybe grouped all this. So these are fluid and test conditions, and we have that length scale. Okay. Well, I'll take the ratio. Reynolds number of the model divided by the Reynolds number of the prototype. I could pretty well see if this ratio is around 1. If it is, great. Then I have the same Reynolds numbers. Okay, so now, so I just substitute. I'll have rho of the water divided by rho of the air. I'll have the velocity that's tested with the water divided by the velocity in the air. I'll have the viscosity of water and the viscosity of air. Then I'll have the length of the model and the length of the prototype. Did that make sense? I hope that's around 1. If it's true, then I conclude the C sub d's are the same. All right, so let's substitute the numbers for rho of the water. That's like 999.7. Rho of the air, 1.582. The velocity in the water, 393 kilometers per hour, and in the air, 700. The viscosity of the air, 1.474 times 10 to the minus 5, divided by the viscosity of the water, 1.307 times 10 to the minus 3. And now, what about the length of the model to the length of the prototype? It's 1/4, is it not? Yeah. And then when you run that number, it comes into 1.000275. It's the same. This is a well-designed problem, so that it's a textbook problem, right? So good. Now we know that the C sub d of the prototype is equal to C sub d of the model. True? Okay, well, what is C sub d of the prototype? That's the drag force on the prototype. That's what I'm looking to solve for, divided by the dynamic pressure, 1/2 rho, 1/2, okay, rho of the air, velocity, air squared, times some area of the prototype. That area is a length of the prototype squared. I know, see, if the lengths are all scaled to 1/4, well, the length times length is an area, so the areas get scaled to 2, but they get scaled as length to the square. That's equal to the drag force on the model, the density of the water, the velocity of the water squared, the length of the model squared. Okay, I'm running out of room, but check. This is sometimes what I do. Do I know what the force is, the drag force on the model is? That's 13,800 newtons, isn't it? Do I know the velocity in the water, the density of water, the velocity of air, the density of air? Yes, I know those. Okay. How about those lengths of the prototype and length model? We know how to replace the ratio of the lengths. And the only unknown in this equation is the drag force on my aircraft, the full-scale prototype that I want to predict. And so I don't know if I can write it out. I'll try and write it out. The drag force on the prototype is the drag force on the model times the density of air divided by the density of water times the velocity of air divided by the velocity of water squared times the length of the prototype over the length of the model squared. And ran out of room, but when you put it in numbers, this comes to be 1,110 newtons, the drag force on the prototype. A lot of times when you have a bluff body and you have high speed flow with a high Reynolds number flow over that bluff body, the wake region and the boundary layer around that flow field are fully turbulent. So what's an example of a bluff body? I don't know, a poorly streamlined car or truck, going through air. It's not streamlined at all. And then it has a big wake region. Maybe here's your vehicle, and it's got a big wake region right in here. And it's fully turbulent in the wake region, and the boundary layer is all turbulent around it. Okay, that's a nice bluff body. Okay, in those cases, the drag coefficient at high Reynolds number is flat. It's not dependent anymore on the Reynolds number. Oh, maybe in here it was highly dependent on the Reynolds number. But out in this region, you would call this region out here to be Reynolds number independent. So somebody says, it's going now a little faster, so the speed went up, the Reynolds number went up. What did the drag coefficient do? Didn't change. I didn't say the drag didn't change because the velocity pressure went up. But the drag coefficient didn't change. Or let's say it goes up even more. Well, the drag coefficient didn't change. Okay. Here's some data. So we have water flows through a long straight pipe. So here's our pipe. It's long and straight. We have a pressure tap to measure the pressure here, the pressure inlet, the pressure outlet. The flow is that way. The length of the pipe is fixed, 1.3 meters long. And the diameter is fixed. It's 10.4 centimeters. The average velocity and pressure loss are shown in the table. So somebody made an experiment. They report those numbers. They moved it. They changed it. They report these numbers. How could they increase the velocity through of water through the pipe? That's what's happening, right? How could they do that? Well, maybe they have a tank of water, and they have it coming back, and they have a big pump, and then they have a control valve, and then they have a straight section, and here is my test section, and then it just dumps it back into the tank. You see that? And maybe this pump is running, and they just open this valve a little more. They let it stabilize. They take some pressure measurements, and they say, hey, that's our pressure drop across that section of pipe. See how they made it? Good. The average velocity and the pressure losses are shown in the table. Predict the pressure loss at an average speed of 80 meters per second. Well, let's see. They stopped at 50. Go back to the lab, get a measurement at 60, get a measurement at 70, get a measurement at 80, and then predict it. Well, that's one way, but what you could do is you then take this data and you put it into dimensionless form. Convert the speed into a Reynolds number. And then convert the pressure loss into an Euler number. What was our Reynolds number? Right down here. Rho V d divided by mu. We're not changing rho or mu of the fluid. We're not changing the diameter. The only way you increase the Reynolds number is faster flow. Faster flow. V is increasing. What about the Euler number? Euler number was the pressure loss divided by the dynamic pressure 1/2 rho v squared. So I know that we're changing the speed and we're measuring the pressure drop, but you compute that and put that on the y-axis. You notice then the data points, the first, second, third. Here's the first, second, third data point. But then fourth, fifth, sixth, seventh, eighth, what happens? Pretty well flat. So what we find is once you're above this threshold, that it's Reynolds number independent. So we anticipate that this Euler number, even when the flow is 80 meters per second, it's still 0.608. So if the Euler number is 0.608 and the Euler number is equal to the pressure loss divided by 1/2 rho v squared, I can get the pressure loss is equal to 0.608, I'm trying to emphasize 0.608 here, times 1/2 rho v squared. So put in the 80 meters per second, put in the density of water, 1,000 kilograms per cubic meter, make the calculation of the velocity pressure, multiply by 0.608, and that will be the estimate or prediction of the pressure loss. So the pressure loss for this problem is 1.9 times 10 to the 6 Pascal. Congratulations, you've now finished dimensional analysis. But let me shut this down and then we'll go over the test, okay?